Hey guys, this is Mr. Lowry. This is kind of some homework help. I'm going to go over your homework for this section 13.3. This was the homework from our day 3 lesson when we talked about spheres. So this page here this is 702. This is the start of section 13-3. Zoom out a little bit for you. And this kind of an important idea on this page is this key concept here. This is the volume formula for a sphere. So the volume is 4/3 times pi times the radius cubed. I know that's kind of hard for you to see, but that's a 3 right there, so a third power. We talked about where this formula came from in class today. Some of that explanation is up here, where it says volumes of spheres, so that's kind of a pretty good explanation. But we watched a video in class that is kind of the same idea. It showed all these little pieces and how they add up. In order to understand that, though, you have to first understand about surface area, because part of what this reasoning uses is this idea that the surface area of a sphere is 4 pi r squared, and if you don't know that, then it doesn't make sense how this becomes this. So there's 2 videos that I posted. The first one is a demonstration of where the surface area formula comes from. And then the second video, you'll see that it uses that surface area idea to come up with this volume formula. So if you miss class, I would recommend that you go watch those video clips. They're not very long. They're about 4 minutes each, or the parts that you're going to watch are about 4 minutes each. And it'll be a good explanation of this formula. Okay. In your homework, you're pretty much just going to be using that formula to solve some problems and find some areas. So I don't think volumes. I don't think it'll be too hard for you. And if you need help getting started, there's some great examples in the book. So first, let's start off with this guy here. I'll just point out what's going on. This is the volume formula, and it uses radius, the radius of what's called the great circle, that circle inside the sphere. So there's the radius, 24. All you got to do is plug it in where the r goes and evaluate. So no big deal. Sometimes you'll get a sphere where they don't give you the radius, they give you the circumference. So in this case, they're giving you c equals 36 centimeters. So you have the circumference of the great circle, right? That circle drawn inside. And you have to find the radius from that. So in this case, what they're doing is they're taking the circumference formula, they're replacing the c with what is given, right, 36, and they're solving for r. You have to do that first before you can use the volume formula, because again, the volume formula uses r. So there's like a problem within a problem. You got to solve for radius from circumference before you can find volume. Okay, one other thing you're going to see is hemispheres. Okay, so hemisphere is a half of a sphere, and this is an example of finding the volume of a hemisphere. Essentially what they're doing is they're just taking the sphere volume formula, 4/3 pi r cubed, and they're just halving it, and you can do the same thing here. So find the volume of the full sphere, and then half it, or divide it by 2, multiply it by 1/2, whatever, and then you'll be able to get the volume of a hemisphere. Okay, so let's take a look at the problems that I gave you and maybe set up some of the trickier ones. All right, so you're starting on page 704. That looks like this. And I've asked you to do some of the odd problems, 9 through 17, the odd ones. So you're going to do 9 and 11, and you're going to do 13 and 15. And then you're going to come over to the next page, 705. And then you'll do 17, and then you start doing more problems. So you're going to do 18, 19, 20, 21, and then finally 28, which is down more towards the bottom. So let's do a couple of those together to help you get started. All right, let's take a look at 13 really quick. So in 13 is one of those problems where we want to find the volume, but they're giving me the circumference. And remember that the volume formula doesn't use circumferences, uses r, radius. And so we're going to have to solve for that. So I'm going to go over to a separate sheet of paper here, move the book for a second so I can write. And this is what we know. Whenever I'm starting a problem that I think is going to be multiple steps, I'm just going to start with the basic idea. I'm trying to find volume. the tool I'm going to use to do that is the volume formula, which looks something like this. Okay, you can also write it as 4/3 pi r to the third. These are equivalent. I kind of like this version better, but whatever. Okay, so I'm thinking I want to use this, but I get to a point where I'm like, okay, in order to use this, I need radius. So I have to solve a separate problem, a radius problem, and I'm going to write what I know about radius. I've been given the circumference, and I know that radius, the circumference is 2 pi times the radius. Okay, so they gave me the circumference of that great circle. Let me show you the picture again. So the circumference is 24. What they're talking about is this guy. And we need to find this guy, the radius, okay, from that circle. So all we're going to do is we're going to solve for r. So divide by 2 pi, divide by 2 pi. These cancel. We also need to put in the actual numbers. This was a 24. So 24 over 2 pi equals r. So 12 over pi equals r. When I cancel out, there's a 2 goes into 24 12 times. So there's my r as an exact number, right? Not a decimal approximation yet. Okay, so there's a problem within a problem here. There's a radius problem within a volume problem. I got to solve the radius problem, solve for radius before I can find volume. Now that I have radius, though, I'm going to plug that into my equation here. So 4 times pi times 12 over pi to the third, right, my radius to the third, over 3. Okay, so that's kind of weird, but let's see if we can simplify. Now, you might go to your calculator at this point, and that will get you the answer. But if we want to practice some of our algebra skills, this will be good practice. So I got 4 times pi, right? And then this guy is going to turn into 12 to the third over pi to the third, using that power of a quotient property. And that's all over 3. Now notice that this pi is going to cancel with one of the pi's down here. There's 3 of them, and now I have pi squared. So I have 4 times 12 to the third over pi squared, all over 3. Okay, let's figure out what this piece is. 4 times 12 to the third, that's going to be a pretty big number. Okay, so that is 6,912 over pi squared over 3. So if I want to simplify that, when I take a fraction, I divide it by 3. That's the same thing as taking that fraction and multiplying it by the reciprocal. And if 3 goes into here, I can cross cancel. So I'm going to see if that works. Okay, turns out it does. So 3 goes into this guy 2,304 times. So this is 2,304 over pi squared. So if you're looking for an exact answer, that's it. On your book, they say they're around the nearest tenth. So let's see what that comes out to be. I'm going to take that 2,304 and divide it by pi squared. Whoops. Okay, and that comes out to be 233.4. And then we just need our units. So my book closed. Sorry, I got to open it up again. I think the units that we were looking for were centimeters. Oh, sorry, inches. So this is cubic inches. Okay, so problems within problems. This is number 13. Okay, just as an example for finding those circumference ones. Also some good practice with simplification. Again, if you get to this point, you can use your calculator to get close enough, but practicing those algebra techniques and getting an exact simplified answer is always good practice. All right, let's take a look at some of the other ones we got in here. So in 15, you're going to have to do a semi or a hemisphere. So find the volume of the full sphere and then divide it by 2 or multiply it by a half at the end, because that's a hemisphere. Don't forget to divide by 2 or multiply by a half at the end. Sometimes you put in everything and then at the end you'll forget and you'll get the full sphere. So be careful about that. Okay, 17 is pretty straightforward. The radius is given to you. They just want you to find the volume. And then 18 is another one of those circumference problems. So we want the volume of the full sphere, but they're giving us this. And so we have to find the radius first and then plug it back in. All right, 19 and 20. Let's take a look at those. 19 is, not too bad. They give you the diameter and they want the volume, but remember that volume uses radius. So you're going to have to take this number, the diameter, divide it by 2. That will give you your radius, and then you can plug that into your volume formula. No big deal. Okay, number 20 is talking about different size, they have a golf ball and they have a tennis ball, and they want to find the difference between the volumes. So the key word here is difference. That means subtraction. So you need to find the volume of the golf ball, and then find the volume of the golf ball and the tennis ball, and then subtract the smaller one from the bigger one. That will give you the difference there. Keep in mind that they're giving you diameter. So just like in problem 19, you need to take the diameter and divide it by 2 to get the radius, and then put that into your formula. Okay? All right, 21 we're going to draw out because I think that's kind of an interesting problem, and I think drawing it out will help. So we have a sugar cone, 10 centimeters deep, that has a diameter of 4 centimeters, and then a spherical scoop of ice cream with a diameter of 4 centimeters on the top of the cone. Okay, so let's draw it out and see what's going on here. So this kind of applies to 21 and 22, but I don't think I asked you to do 22. So 21, we got a cone, and we know the cone is 10 centimeters, was it? Yeah, 10 centimeters deep. So that's basically the height of the cone is what they're giving us right there. So this measurement from the top of the circular base. Now, this cone wouldn't actually have a base here. It's going to be like kind of hollow. But if there was a circular base, then it would be measuring from there. So that's 10 centimeters. And then the diameter of that is 4 centimeters. Okay, now we have a spherical ice cream scoop. So what's going to happen here, since the diameter of the ice cream is the same as the diameter of the cone, the biggest part of the ice cream cone is going to be sitting here. So you're going to have a hemisphere on top, and you're going to have a hemisphere on bottom. So this spherical ice cream is sitting in this cone. Okay? The question is, if all the ice cream melts into the cone, will the cone overflow? So basically the idea is the volume of the ice cream bigger than the volume of the cone? And if it is, then it's going to overflow. So let's kind of, again, write down the basic idea to start with. So is V sphere greater than V cone? If that is a true statement, then we're going to be overflowing. Okay? So we need to find, in order to answer this question, if this is the case, we need to find V sphere, and we need to find V cone. So I write out, basically two separate problems here that I'm going to have to answer before I answer that original question. So V sphere, volume of the sphere, is 4 pi r to the third over 3, or 4/3 pi r cubed. And in order to solve this problem, I have to know r, right? So look at these layers. Here's the original question. Here's a sub-question. Here's a sub-sub-question, right? Once we figure out the radius, then we can figure out the volume of the sphere, and then we can figure out if it's bigger than the volume of the cone. Okay, so the radius of the sphere is half the diameter, and they told us the diameter is 4. So the radius is 4 over 2, or 2 centimeters. Okay. Now that we have the radius, we can go back and find out what the volume is. So 4 times pi times 2 to the third over 3. 2 to the third is 8, so this is going to be 8 times 4, 32, times pi over 3. Okay, that is the volume of my sphere, my spherical ice cream. Okay, now we have to find the volume of the cone. So we've answered the sphere volume question. Now we have to answer the cone volume question. And if you recall, the volume of a cone is 1/3 times pi r squared times h, where h is the height of the cone and r is the radius of the cone. Another way to write that is pi r squared h over 3. Those are equivalent. So, again, sub-questions. Before we find the volume of the cone, we got to know what the radius is. Again, the radius of the cone is 4, just like the ice cream. So we got 4 over 2 again. The radius is the same for the ice cream and for the cone. We also need to know the height of the cone. They tell us it's 10 centimeters deep. Okay, kind of a different word, but that's basically the height they're giving us there. All right, so we got that, and now we can plug all that stuff in. So we have r, we have h. We're going to have pi times 2 squared times 10 over 3. So 2 squared is 4, times 10 is 40. This is 40 pi over 3. Now you could punch this into the calculator if you wanted to, but if you notice, they both are divided by 3, and they both are multiplied, like we got a number multiplied by pi and divided by 3. So the pi over 3, that's the same. The only thing that's different about this is multiplied by 40, and this is multiplied by 32. So this is clearly the bigger one. That means there's more space in the cone than the ice cream has. So if you think about it, like there's all this space down here, right? The cone is like kind of a bunch of empty space. And as the ice cream melts, it's going to fill up that empty space. And since the volume of that ice cream is less than the volume that the cone can hold, it's not going to overflow. Okay, so it says explain, right? This is obviously what you want to show. You have to show, look, I found the volume of the sphere and I found the volume of the cone, and the volume of the cone is bigger than the volume of the sphere, so it's not going to overflow. That's your explanation there. Okay, so 21. All right, one more I wanted to look at was sorry, I lost my train of thought. One of the ones I wanted to look at was 28, which is the tennis ball problem. So let's take a look and then we'll draw it out. Find the volume of empty space in a cylindrical tube of 3 tennis balls. The diameter of each tennis ball is about 2.5 inches. The cylinder is 2.5 inches in diameter and is 7.5 inches tall. So I don't know if you guys have ever seen a container for tennis balls, but they're cylindrical. So what you have is something like this, a tube, and then you have like 3 tennis balls inside. Okay, so let's just conceptualize what's happening here. Let's do the basics of the problem without any math, just understanding in words what's happening, or maybe symbols. Okay, so we want the space in between the balls, the space between the cylinder and the tennis balls. So what we need to do is we need to find the volume of the cylinder, and then we need to subtract the volume of all the balls together. And since there's 3 of them, it's 3 times the volume of 1 tennis ball. So volume of the cylinder minus 3 times the volume of 1 of those balls. This is the question we need to answer. What is that equal to? Okay, so let's do a sub-problem. Let's find the volume of the cylinder. Okay, start out with my formula. It's going to be pi r squared h. So we need a height. They told us it was 7.5. And we need an r radius. We know that the diameter of the ball and the diameter of the cylinder are the same. That ball is going to fit kind of right against the sides of the cylinder. But we know the diameter is 2.5. So if we divide by 2, we get 1.25. Okay. Now, you can use the decimal version if you want. They started with decimals, so that kind of makes sense. The problem with decimals is that as you square them and get them bigger, the number of decimal points that you have usually is going to increase. And so it gets harder to kind of keep track of exact numbers. So the other option is to change it into a fraction, and you could use that fraction. So either way is okay. Let's just kind of plug it in and the decimal, since we started with decimals here. We're not, the book isn't interested in giving an exact answer, although that's a good practice to know how to do. So let's do the cylinder again. We're still in cylinder land. We got pi times r squared. Now we know the radius is 1.25. Okay, and we're going to square that, and then we're going to multiply that by 7.5. Okay, now this part, the 1.25 squared times 7.5, that's actually going to be a rational number. It will be a long decimal, though. It will terminate. It's like a terminating decimal. So let's find out what that is. Okay, so 1.25 squared, and multiply that by 7.5. And that's the fraction version. Okay, if you change it into a decimal, that's the decimal version. But notice that it stops, right? It doesn't continue on. So this is actually a rational number because it terminates. So if we wanted to, we could write this as like 11.71875 times pi. Now typically, if somebody's asking for an exact answer, this is kind of clunky. They would probably rather have it as a fraction times pi. But for our purposes, we're not, this isn't the final answer. We're just trying to find, the difference in volume anyway. So we're going to leave that as the volume of our cylinder for now. Okay, now we have to find V ball, the volume of each of the tennis balls individually. And we know that formula is 4 pi r cubed over 3. So we need an r, right? We got to figure out what r is. We kind of already did that, though, because the radius of the ball is the same as the radius of the cylinder, which is half of its diameter, or 1.25. So using that in the formula for volume of the sphere, we got 4 times pi times 1.25 to the third power all over 3. Now the tricky thing here is when we divide by 3, we're actually going to end up with it's still a rational number, but it's a repeater. It's going to be a repeating decimal. So let me show you what I mean. 1.25 to the third power. Okay, that's the fraction form. Change it to a decimal. Okay, so notice it terminates. It's rational. Okay, if I want to take that number and multiply it by 4, okay, there's the fraction version. There's the decimal version. So again, it's rational. It terminates. Now if I divide that by 3, I still have a rational number, but when I try to change that to a decimal, that's a repeating number, right? So this is like 2.6041666666666 forever. It's still rational because it repeats, and we still have to multiply it by that pi number. So this right here is the exact volume of the cylinder. This right here is the exact volume of one of the balls, but remember we need to multiply this by 3. And the nice thing about that is since this is a divide by 3, when we take this and we multiply by 3, it's going to cancel that 3 out, and we're going to lose that repeated number. So let me kind of write this out for you and show you what we got going on. So the V cylinder, 11.71875. Now that is an exact number. That's not rounded at all. Times by pi, which is going to make it irrational. And then I want to subtract 3, because there's three balls, multiplied by the volume of one of those balls, which is 2.60416 repeating times pi. Now that's a little clunky, right? If we were writing an exact answer, this wouldn't really fly. You'd want that as a fraction. But again, this 3 is going to kind of change things up. So let's multiply that by 3. Remember, this is not including the pi. This is like the volume of one of the balls. So I'll multiply that by 3, and that comes out to that nicer number. So the volume of the cylinder, still 11.71875 pi, right? All 3 of the balls together is this number, 7.8125 times pi, because I didn't bring in the pi yet. Pi is irrational, and so it's gonna basically turn any other number irrational when you multiply. So this is more or less what we got. Now again, if you were putting your answer as an exact answer, you typically wouldn't use decimals. Even if they're not rounded, you typically are going to use fractions, just as a convention. But let's do this. Let's see what we got here. So 11.71875 pi minus 7.8125 pi. Okay, so they didn't tell us what to round to, but since they started out in tenths, like 7.5 and 2.5, we'll probably give the answer in tenths. So 2.3, and this was cubic inches. Okay, so conceptually the problem's not too complex. What gets really hard is they started out with decimal numbers, and so trying to keep our answer exact when they started out with decimals is kind of a challenge. You can still do it, and it's good practice, but you probably could have gotten by using a calculator here, as long as you were careful with your rounding, and it would have been okay. So anyway, that's number 28. Again, learn how to break these down. That's the problem-solving technique that I hope you leave this class knowing. Start out with a basic idea that you need to find, and then create sub-problems for yourself. Break this up into small, manageable pieces. If I asked you to find the volume of a cylinder, you'd be like, yeah, no problem, I can do that. If I asked you to find the volume of one sphere, you'd be like, yeah, that's no problem, I can do that. Okay, so then you should be able to do the whole problem if you break it out. Cylinder, ball, multiply it by 3, subtract them. There you go. Okay, so I hope that helps. Practice your organization, practice your problem-solving skills of breaking it down into pieces, because that's the real important lesson that I hope sticks with you. Thanks for watching, guys. Have a great spring break.